So my name's Alex Bertram. I work at a company called Be Data Driven. We're based in The Hague. I'm going to share a couple things about Renjin today. I realized about halfway through preparing the slides that I have maybe 2 to 3 presentations actually. So I'm going to skip quickly over some subjects, and if you're interested, then we can come back to them during the questions or later in the afternoon. But today I'd like to introduce Renjin very briefly, and then I want to talk about the role of compilers in the Renjin project. And then give kind of an example of 3 ways in which we use compilers to make Renjin possible, and give some examples of how they work and what role they play in the project. So first up, what is Renjin? Renjin is the JVM-based interpreter for the R language. It's written in Java. It runs on the Java virtual machine. Basically, it inherits a large amount of code from GNU-R, so nearly all of the packages with some light modifications. Also, the amazing NMath library and the APPL library, we've incorporated those into the project. Basically, what we're replacing is the GNU-R interpreter, the bytecode compiler, the garbage collector, and the other infrastructure that actually runs the code. So Renjin has an interpreter, an AST interpreter. It has a just-in-time compiler, and it runs on the JVM, which provides garbage collection and other runtime support. So Jan was talking about how quickly time flies and the realization that we've been working on this for a while, and the same is true with Renjin. I think it was about 8 years ago that I threw up something on Google Code at the time because I was working for a customer and trying to get a random forest model to run on their servers, and I could not for the life of me get a Fortran compiler to build on Solaris 8 or something. And so I thought, you know, wouldn't it be great if this all ran on Java like the rest of our projects? How hard could it be? It's famous last words. But I put up something. I had I got something running quickly. Put it on Google Code, and before I knew it, people were looking at it. And I got an email from Helena 8 years ago saying, "Dear Mr. Bertram, I am looking at your project, but are you aware that it runs 50 times slower than GNU-R in this piece of code?" I was not aware of that. So I learned a lot about compilers and about runtimes over the last 8 years, 9 years, mainly through groups like this, gathering through like this, from Jan and from others. So it's really a privilege to be here. But in the meantime, Renjin has grown up. It works, it runs, people use it. We've just put up a new website that focuses on some of the case studies of how people, companies, researchers use Renjin to, for example, deploy their code together with our applications on the cloud, so they don't have to install Fortran compilers, for example. We have, for example, it's incorporated in a business intelligence suite that's used to supplement a commercial software product with the ability to run R in their product. So it's quite cool to see the project actually kind of come together. And I want to talk a little bit about how the project changed and what made that possible. Because when the project started, well, you had a bunch of C code over here. And I wanted it to run on the JVM, so I went over and I found the file that does do eval, and I went over to my terminal and I basically took that from C and I turned that into Java. And then I did that again for another file, and then some other people came along and they did it for some more files. And that got things working okay, but at a certain moment you start to realize how impressive this project is. And by this project, I mean GNU-R and the R ecosystem. So there's some of the code, like the interpreter, that's interesting to replace and to rewrite and to think about ways to improve it. But there's a lot of really good code that is not easy to simply rewrite. So all of the numerical analysis, there's been an enormous amount of thought that's gone into that. If you're interested in packages, I mean, this is a snapshot, I think, from last year. 17 million lines of code, of R code in CRAN, but also 8 million lines of C, 5 million lines of C++, and nearly 2 million lines of Fortran. A lot of which is highly specialized domain knowledge. I mean, I wouldn't dare to try and rewrite that. So it became clear gradually that if this project was to work at all, there had to be some automation behind it. There had to be some kind of transformation, some kind of compilers, because otherwise, first of all, I would never have the time, even with a small group of people contributing, and also, why would you want to do that? Why would we want to take the work of Martin Meckler and redo it, but worse, with all the same bugs that he's probably fixed over the last 20 years? So, yeah, we started very slowly to build some tooling around GCC, and so the way that I've learned that compilers work is that they take something high level like C code or C++, and they start turning it into simpler and simpler things. So I have an example here from one of our logging outputs from the NMath library. If you can see this, it's a bit hard to... But here on the left you have some C code, and GCC, what it does is it turns that statement, right? That's kind of a complex statement to understand, to analyze. So it's 3 statements there. It turns it into a simpler set of what's called 3 address codes, or in GCC it's called Gimple. It probably looks a lot similar to what Jan was showing, or almost like the disassembler from the bytecode compiler. The idea is that you want to turn it into something simpler so that it's easier to understand and analyze. And once you've got it in this form, then you can start, at least on our side, we could start to build the tooling that translated this into Java bytecode. So, we have a statement, if the x is basically not a number, then go to basic block 5, and in Java, in the JVM bytecode, we call a method, we invoke a static method, double is an A. If it's not equal to 0, then we jump. So it's a very mechanical translation, and suddenly the challenge of repurposing, of reusing this code seems a lot less daunting. And I think for me that's been really transformative. This idea that this code is really much more malleable than we think of, right? So there tend to be flame wars on Twitter or on Hacker News about, oh, this project is being rewritten in this language, or this project is much better, it's going to be in Rust, and it's going to be so much better than it was in C. Yeah, maybe it is, but life is too short to rewrite code, I mean, as far as I'm concerned. And the possibilities, once you start looking at these kinds of technology, if you've got good code that's been battle tested, that works, there are other possibilities. And so we built a pipeline that takes C, C++ files, Fortran files, runs it through GCC. GCC turns it into Gimple, and we wrote a plugin that turns that into JSON, so it's easy to parse, so you just get this nice big JSON tree. And then we have the GCC Bridge compiler that turns that into Java class files. But there are still some challenges, right? So pointers. The C memory model works a lot different than Java. Java is garbage collected, right? So you ask the runtime for some memory. It gives you that kind of memory, but you have to tell it what type of memory. You have to say, I want a contiguous array of double precision floating points. And once you have it, you can't just pretend that it's an array of integers, right? The JVM doesn't like that. It enforces certain rules. So that's a challenge, right? So one approach is the kind of what's called the big bag of bytes approach. So the idea is in Java, you just say, okay, well, I'm just going to allocate a bunch of bytes. This is going to be my memory pool, and I'm going to write a malloc function, and that's just going to give me a slice of those bytes, just like the C runtime would. And then I have to, I just basically set these bytes to the doubles. I read them as doubles at the offset. So that works perfectly. But for our purposes, it's not very good, because that means that we have 2 worlds. We have one world in which all of the native code lives and it has all of its memory. And we have another world where we have our Java data structures, maybe a Renjin character vector or data that's coming in from the Java world. And the only way that those 2 pieces of code can communicate is if you copy them between those 2 groups of memory. And that's not a great idea. That's not what we wanted to do. So we started looking at different strategies for basically transforming this memory model into a memory model that works in the JVM. The first one is the fat pointer strategy. The idea is that you do some analysis to figure out what kind of memory is being allocated. So in this case, we could tell that the malloc was being assigned directly to a double pointer. So we allocate that as an array of doubles. We add an extra variable to keep track of the offset within that thing so that we can do pointer arithmetic. And we work with arrays. So for Fortran code, this works really, really well. It's super fast. The JVM loves this kind of code and can compile it to very fast code. So that was the first kind of iteration, and we compiled a bunch of Fortran code, which is good because I don't understand a word of Fortran. Yeah, C is awful. Yeah, C is cheats, it lies, and it plays tricks. So I always thought that C was statically typed, but actually it turns out you can really do whatever you want with memory in C. So, for example, in this line I've defined a structure with 8 bytes of double precision, followed by 4 bytes of, a 4-byte pointer, followed by a 4-byte integer, followed by a 4-byte pointer. But yeah, the code can just allocate whatever it wants. It doesn't have to be an even amount of these, or 1 or 10. It could be 1.5. And believe me, this code is out there, and sometimes for very good reason. I mean, but sometimes for less good reasons. But the point is that we can't rely on this. So the next iteration of the project introduced this idea of a virtual pointer. So the idea is that whenever we saw a pointer in C code or in Fortran or C++, we just said, okay, we're going to give you a Java object that knows how to do certain things. So, for example, this object knows how to pointer plus, right? So if you want this pointer plus 8 bytes, it will give you a new pointer. If you want a byte, if you want to set a byte, if you want to set a double, if you want to set a float, whatever, we'll just do that. And so this allows us to work around and to paper over the differences between the memory models. So basically, D becomes a reference to a pointer interface. We have a helper method that allocates a pointer of type double, and we can use these. We call these as methods. Now, in this case, the JVM is pretty good. It will JIT this. It will unwrap this and turn this into pretty fast machine code. But sometimes it's not possible to. Sometimes it's not possible to determine what kind of memory is being used, or sometimes it's being used as a double, sometimes it's being used as bytes. For, like, for example, the digest package, you give it an array of doubles, and it looks at that byte by byte by byte in order to compute the hash. So in those cases, we do see a performance slowdown. That's definitely a downside. But it does give us a lot of freedom, and this was kind of an upside that we didn't expect, is that by basically substituting all of the pointers in these packages, in these 8 million lines of C code with these virtual pointers, we can do anything we want with character vectors, with double vectors, with R objects, right? So in GNU-R, they're working on a project right now called the altrep to allow, for example, a sequence of 1 million integers not to be stored as an array, but as a function which just gives you an individual value. Now, that does mean that a lot of code, C code, has to be manually updated to accommodate, right? Because it's not always going to be an array. Sometimes it might be stored somewhere else. But here we're able to do that automatically and basically transform the entire CRAN and bioconductor code base to work with a new implementation and optimized storage of the vectors. So that's an upside. The other thing we can do is that we can do some automated API migration. So, for example, one of the things that you'll see often in C code is that the code will allocate a pair list, and then shortly thereafter change it into a function call. Now, that's possible because in GNU-R, a function call and a pair list have the same memory layout. So all you're doing is setting a flag and saying, okay, this is not a pair list anymore, this is a function call. But in Renjin, we wanted to do a lot more with function calls, right? So we cache, for example, an argument matcher that has some information about whether the arguments are named. We cache the call site, so our memory layout is not the same. So all of a sudden we had a thing where it's like, first they tell you I want a car, and then they say, oh no, turn that into like a 747, right? So for us that was we can't do that. We can't do this set type of. But with automated transform, we can actually recognize that sequence. We can do the flow analysis and realize that even though it's allocated as a list, it's actually being set as the flag is being set, and we can replace that at compile time with the appropriate alloc lane call so that it's allocated as a function call to begin with. So this is really powerful. It's certainly helped our project a lot, but I encourage everybody to think about how not everything has to be manual. The code is a lot more malleable and changeable than sometimes we think. So the last example is we compiled a graphics and GR devices package to Java bytecode, but there's a problem for us is that those packages use a lot of global variables, right? So you set a graphics device and that sets the active device for the process, for the entire process. So if you're running on a web server and you want to generate charts concurrently or plots concurrently for two different requests, you can't do that, or you wouldn't be able to do that because they would be overwriting each other. But this is also a case where we're able to transform those global variables automatically to thread local variables. So this is kind of the pseudo Java. Basically we take where there's our current device is a global variable, and we replace that with a function call which says, get me the current device for this thread, which means that we're able to run multiple sessions concurrently and serve requests concurrently with a far lower memory overhead than if you would be running them in separate processes. Okay. So that's one example of how we're able to use these kind of compiler technologies to repurpose code, to take code that is excellent, that's high quality, and make use of it in new environments under new constraints. The next thing that I want to share is more of an experimental approach. So the GCC bridge, that's very much in production, and if you go to packages.renjin.org, you'll see all the beautiful G2 plots that are produced from this transform code. But what I want to share now with you is a bit more experimental. This is a just-in-time loop compiler for R. So it's very much along the lines with the similar goals as to what we heard from Luke and from Jan this morning. The idea is, how do we take our code and analyze it and then optimize it to run it in a faster way. So this, you can actually open up RStudio and just source this install script if you trust our web server, and load this as a package and just run this as kind of a toy in your R session. And basically what it does is that it's an optimizing compiler for R, but it's a very selective optimizing compiler. It sets its ambitions. The rationale is there's a lot of code that doesn't need to be fast in R, that's doing other things. But when we hit a loop with a large number of iterations, then we can be pretty confident that that's going to need to be fast. And what's more is that often these hot paths, they tend to be relatively simple. They don't tend to use a lot of dynamic dispatch or crazy stuff, as Jan said. So we have a better chance of being able to analyze that code statically. So the way that we do this, I want to introduce this by just looking at a very simple example of constant propagation. So constant propagation is a technique where you basically look at things that are known at compile time and just push them through your assignments in your code. So you'll see at the top we have two constants A and B, where A is assigned to a constant 3 and B is assigned to a constant 4. And then C is A plus B. So in this simple example, we can just push those constants down, right? So we can say, all right, every time I had A and B, I'm going to replace that with 3 and 4, and you keep going. So then you have this branch that becomes constant, right? So then you don't even need to jump, and you know that this branch has to be taken, and you end up with a completely optimizing all the code. So that's just a super simple example, but that's kind of the traditional role of constant propagation. But what's fascinating is that you don't need to you can use this for more than just constant values. You can use this for other properties, right? So things like types. So maybe we don't know what A and B are, but maybe we know that they're both double vectors of length 1, right? And if we know that, and we have a set of rules about R's built-ins, then we can make some deductions in the same way that we propagated those constants, right? We know that if you have two double precision vectors without attributes, and you add them together, you're going to get a double of length 1 without any attributes. We know that absolutely. In the same way that we know that if you, then C is now a double of length 1. And so then you know that C times 2 is still a double of length 1. So we can take things that we know about various values and various values and use that to specialize the R code to compile that down to something more efficient. So just to give you an idea of the kinds of things that we propagate or that we're looking to analyze, these are a selection of some of the properties that we're tracking, right? So when the compiler sees A and B at the beginning of a loop, it's going to look to see, are those positive, right? Because if they're positive and they're used as index subscripts, then we know that we can use those, we can do a quick index without having to check to see if it's negative, for example, which would, if it's a negative index, then you get something completely different. Do we know that it has a non-zero length? Do we want to know that it might have a class, right? Because if it might have a class, then we know that we have to be careful. So there's all these properties that we can track, and using the rules that we know about the primitives, we can propagate those to all of the different values in expressions within the compiled code. And what's great about it, what's very nice about a just-in-time compiler is that at the point that we enter the loop, right? So the interpreter is interpreted Z, it assigns 1 to 1 million, it assigns S to 0, and then it comes to the for statement and says, aha, I'm going to have to do this 1,000,000 times. So let me stop for a second and see if I can optimize this loop body. And at this point, you know a lot about what's going on. R is difficult to analyze statically, but at runtime, you have a wealth of information. We know that we can assume that, well, we can say that S is a scalar. And we know its type. We know whether it has attributes or not. And we can use that to translate that into our intermediate code. So very simple straight line code. And then propagate all of those properties. And by doing that, we can build the control code graph. And as long as the code obeys certain rules, then we can analyze this and optimize this just like it were C code, right? We can use all of the classical, like well-established rules for optimization. Transform into SSA. You do the type inference based on the values that you have. This is all great papers, very very accessible, and we just have to be very aggressive about bailing. And this is the one downfall of this approach, is that there are many things that can cause an abort, right? So if you get to that loop, you've done all the analysis, but one of the functions changes during the execution of that loop, then our algorithm is like, I'm done. I can't go further. If you have what we call our black holes, right? So you have certain functions which are black holes. They completely undermine our ability to predict anything, right? So like this environment, then you know that suddenly the environment is floating out there, around there, and anything can happen. Sysparent, reassign, but there's a finite number of those, and if we encounter those, then we bail, and we go back to the interpreter. So, but if we get past that point, if we don't bail, and we can analyze it statically, we know we can identify all the functions, then we can turn this, for example, we don't have to store scalars as without attributes as an S expression. We can store it as a floating point in a machine register. So it can be just as fast as C code or C++ code. So I'm going to show some timings. These timings are intended to be illustrative, right? So these are examples that are selected to illustrate how this works. It's not an argument that this is a better approach than any other, because there's a lot of variance. But in a loop like this, where you have many iterations, and you have scalars that can be that don't have to be boxed, right? We can store those as regular floating points in machine registers. I mean, you have least a factor of 25 speed up over the baseline interpreter and 12 over the bytecode interpreter, because we have more information, right? At compile time, there's a lot you don't know about what's going to happen, but at this point in time, at runtime, we know nearly everything. If you add S3 dispatch into the mix, then I mean you can make this example as explosive as you want, but the compiler it can deduce it knows that X now has the class of foo, so it can statically recognize that that X is that there is no function defined for plus.foo, and it can use the normal addition, right? So it doesn't have to. Otherwise, you have to check every iteration of the loop. Hey, is there a plus.foo? Is there a plus.foo? Is there a plus.foo for 1,000,000 times? So if you can assess at compile time that there is no plus.foo, then now you have a speed up in the area of 60 times, right? So it's very powerful. If you add function calls, oh boy, if you add function calls, right? This is my question for Jan earlier. This is a very simplistic approach, but we just inline the hell out of everything, right? So we see a function called the half square, we identify which function it is, and we inline it, and we can pass all of our values through that function so that we know what's going on there. And so then you have no overhead, you have no promises, but again, it's limited in the sense that if one of these arguments was stop with side effects, then we'd have to give up, right? So we can only do this inlining if we can be sure that the arguments have no side effects. So some significant limitations. So this is a now I find micro benchmarks very, very hard, but what we did was we collected some samples from the RCPP website where they have like, oh, this is the R version, here is the C++ version. So that we could compare not just R with GNU R with Renjin, but Renjin or the GIT with handwritten C++. So you can say that it's hit or miss. Well, it's not bad. In some cases we approach. This is a logarithmic scale, so RCPP has nearly a 10 times speed up over the bytecode interpreter, and Renjin is like 8 times. For this Leibniz, I think it's calculating pi or something. The RCPP is 60 or 70 times, and we're 50 times. But if you have to bail, if one of our assumptions, one of our constraints is violated, then it doesn't help you at all. So that's kind of the limitations of this JIT compiler, and that's why it remains experimental. We haven't merged it into the release because, the first thing is the testing is difficult. We have 40,000 unit tests for Renjin, but none of them exercise the GIT compiler because they're not in loops, right? So how do you write tests to make sure that the interpreter is correct, but then also the GIT, right? So that's a big problem. How to test this, how to make sure it's correct, that it doesn't degrade in performance. And as you saw in the graph, it can have a huge impact if the stars align, but if the stars don't align, then you don't have any impact. So So the question that we've been looking at over the last month or two is, what could we achieve if we reined in our ambitions a little bit? So what if we were a bit more modest in what we tried to do with the compiler? So we've been looking at, could we come up with a way to compile R to Java bytecode in every single case, just across the board? And we've started from the exact opposite side of the problem, which is, how would we do this if we applied zero optimization, just for the simplest, dumbest compilation to Java bytecode? And that's interesting for a couple of reasons. One is it means that we can test a lot more of it with our unit tests, because our unit tests will be hitting the compiled code for every single test. So that gives us a bit more confidence in the compiler. The second thing is that apart from the performance benefits, it comes with huge developer upsides. So already I can open up IntelliJ and I can debug C and C++ code, step through breakpoints and examine variables because it's just compiled to Java. And if I can do that with R, then that's also kind of a big win. Just being able to use the normal Java profiler so that R actually would become a first-class Java language. So for us, that's also an interesting aside from the performance. So we built this ahead of time compiler, which just it basically does what the bytecode compiler does for GNU R. It maintains a pool of S expressions that are needed to pass to as function calls. And we use the Java bytecode the best that we can. So you'll see here there's an invoke virtual to evaluate the function, to look up the function basically. This is accessing a constant from the constant pool because we need to pass the original call to the caller, and then creating promises from the environment and passing that to the function that we find. So this almost passes all of our tests, and we see about a 20 to 30% speed up, which is okay. The code size is a lot bigger, so we need to work on that, right? The zip file goes from I think 25 megabytes to like 40 megabytes, just because we have these huge constant pools and a lot more bytecode. But the JVM is pretty good about managing that for us. So that's something that's going to be rolled into the new release, just so that for ease of debugging, so that people it's like a first-class citizen on the JVM. And then we're turning our attention to what we can do, what kind of optimizations can we apply on top of this. And so this involves basically extending some of these models, these constant the tools to accommodate the quirks of the R language. So, for example, this whole question of having the C34 plus C, right? So in this context, the first context, we resolve to a function, and in the second context, we resolve to the local variable. So one way to do this is to actually rewrite this in our intermediate code as an assignment to C as one, but then to treat that function with that variable that's used in the function call as a completely separate variable. But it's just that assigning to C may or may not have the side effect of assigning to C star if C is a function, right? But then we can use the same type propagation logic to see, okay, we can clearly see that the compiler can see that the type of C is not a function, and so then this branch is eliminated, and C star remains bound to the function. So that's some of the ways that we're exploring to kind of integrate the semantics of R into these kind of classical models of type inference and value inference. But that's it. I'm out of time, and I'm actually at the end of the presentation. So I encourage you to go to www.renjin.org. We just released today the 3.5, the beta version. So you can download it here, a command line version, or if you're a Java developer, you can add it to your project very quickly. Yeah, the packages are in the process of building, and we'll do a final release with hopefully all of the bugs fixed at the end of the month. But I mean, you can see the results of this compilation process is that. Yeah, I mean it works mostly. No. Consider code malleable. It's not as rich as you think, and before you rewrite, think about transforming, and yeah, think about the Renjin project in your work. Thanks.